All right, here we go again. Here I go again on my own. In this video, I'm just going to be reviewing several numbering systems that you may see in embedded systems or digital logic. And I'm going to start with binary, which is perfect for representing digital logic because the possible states of a binary number are either 0 or 1. And if you know anything about digital logic, you know that a 0 typically represents a false value and 1 typically represents a true value if you're using positive logic. In that case, we can use a binary number system to represent decimal numbers which are in base 10 that we're much more familiar with. And the reason that we might want to do that is it makes information readable for machines and microcontrollers, embedded systems, all those things. So what you see in front of you is a poorly drawn circle that is trying to communicate for 4 bits what are all the possible represented numbers and how do those show up in terms of binary. So 4 bits means that there are 2 to the 4th possible values. That's 16. We always start counting from 0, so that means I can go 0 through 15. If we add another digit in binary, then we can go even higher, and we'll talk more about that a little bit later. The reason that I have this represented as a circle is that if you add numbers that are bigger than the numbers that you can possibly represent, what happens is you get an overflow. So let's say, for example, that I added 8 and 8. Well, 8 and 8 is 16, but the highest that this numbering system goes up to is 15, so it's going to overflow, and my computer is going to think it looks like 0. And the ways that we deal with this, those will be handled a little bit in another video. But I just want to get you familiar with that concept. We're going to start by converting numbers from binary to decimal. The way that this works is I take my binary number, let's say 1011 base 2, and I can represent what's going on by looking at place values. So up here, this would be our 0th place, our 1st place, our 2nd place, and our 3rd place, which means that what's going on here is 2 to the 3rd, this is 2 to the 2nd, this is 2 to the 1, and this is 2 to the 0. So if you want me to do that, that's 8, 4, 2, and 1. So the conversion, let's go back to my normal color. Beep, bleep, bleep. So the conversion would look like this. I've got 1 times 2 to the 3rd plus 0 times 2 to the 2nd plus 1 times 2 to the 1 plus 1 times 2 to the 0. So that's 8 plus, 0 plus 2 plus 1, and that's equal to 11 base 10. Right, one more just for grins and giggles. Let's say I've got 1100 base 2. Let's convert that. That would be 1 times 2 to the 3 plus 1 times 2 to the 2nd plus a whole bunch of zeros. That's equal to 8 plus 4, which is 12 base 10. Similarly, we might want to go the other way, going from a decimal number that's unsigned, doesn't have a positive or a negative, but from a decimal number and taking that to binary. We're going to use the divide by 2 method. Best way to see this is using an example. So let's say I've got 52 base 10 and I want to represent this using base 2 or binary. The way that I'm going to go ahead and do that is I'm going to take 52 and I'm going to divide by 2. And the result of 52 divided by 2 is 26. And I'm going to make a little column over here for the remainder. So the remainder of 52 divided by 2 is 0. So we'll divide by 2 again. Now I get 13. and the remainder is again 0. I'll divide by 2 again. Now I've got 6 with a remainder of 1. So 2 times 6 is 12, plus 1 is equal to 13. Then we'll divide by 2 again. I've got 3 with a remainder 0. Divide by 2 again. I've got 1 with a remainder 1. Divide that by 2. Because I want to go all the way till I get to 0. 2 can go into 1 0 times. Remainder is 1. And then to get my binary number, I'm going to assign the most significant bit at the bottom and work my way down to the least significant bit, which is at the top. So the binary representation of 52 base 10, the decimal number, is 110100. And once I clean that up, I'll put a little base 2 down here just to help me know that that's a number that is in binary. So that's the same as 52 base 10. And I just want to highlight that this representation has the fewest number of bits that I can use. So this is a base 6. So this is a 6-bit binary value, which means that the largest place is 2 to the 5th. So 2 to the 5th is here, and this is 2 to the 0th down there. So if I add all these things up, what is 2 to the 6th? It's equal to 64, and that means that my numbers can go from 0 to 63 that I can represent. So if I went down by 1, let's say to 2 to the 5th, I would get 32, which means I could only represent from 0 to 31. Perfect. One more quick example. Let's show you. Let's say I want to represent 24 in binary. So I take 24, divide by 2. I get 12 with a remainder of 0. So make that remainder over there. 2, that's 6. This is 3. Still doing good in terms of remainder. Divide by 2. Now I've got 1 with a remainder of 1. Divide by 2. Finally get to 0. So that means the binary representation of 24 is 11000 base 2. In addition to binary, I just want to talk briefly about hexadecimal, which is a compact way of writing binary using fewer digits. So hexadecimal is base 16. And essentially, the easiest way to think about this is if I have a 4-bit number in binary, I can represent that 4-bit number. 2 to the 4 has 16 possible values. I can represent that using a single digit. What that means is I'm going from 0 to 15. Now, from 0 to 9, we have digits that work super great. The problem is what happens when I get to 10 in base 10. Well, that adds a place, and I want to represent things using a single digit. And so from 10 to 15, I'm going to use the letters A through F. And so if I had 15 base 10, so a decimal number, that's equal to F. If I had 12 base 10, that's equal to C. Now, how can we do this in a way that is sort of easy for our brain to understand? One of the ways that I think about it is I take a binary number and I just look at it in 4-bit chunks. So look at 4-bit binary chunks. So, for example, if I've got 000, well, that's just equal to 0 in base 16. If I have 1111, that's equal to F in base 16. And if I had an 8-bit number that's composed of those two, then the resulting hexadecimal would be F0 base 16. working out how to get the decimal from this is similar to binary, so that would be equal to 15, that's what f is in decimal, times 16 to the 1, plus 0 times 16 to the 0. That's equal to 240. If I had a 16-bit binary number, if it were all ones, the hexadecimal representation would be equal to FFFF. So I've taken my chunks of 4 and split them up. And I could, again, calculate the decimal value of that. That would be 15 times 16 cubed plus 15 times, that's a times, not an add, times 16 squared plus 15 times 16(1) plus 15. Turns out if I add all that up, I get 65,535 values, or I guess that's the max. The number of values goes from 0 to that number, so I've got 65,536 total values that can be represented, and that's 16 bits of binary data that's represented compactly using 4 digits in hexadecimal. This is really common when you're working with embedded systems, microcontrollers, and you're just trying to communicate with your machine in a way that will make sense to the compiler and make sense to the linker and interpreter, all those things. So it's important to see how this works. So one last note is just in, there we go, last note is in C or C++, we have prefixes for binary and hex. So for a binary number, we use 0b for, so this is binary, and for hex, we use 0x. This is not an O, it's a 0. I don't know, I'll put a line through it so you can see that's a 0. That's probably worse. All right, so in other words, if I had 0b1111, that's the same as 0xf, which is the same as 15 in decimal. So that's just something that you should note. If you're typing hexadecimal, you need to signal to your code that it is a hex number and not a decimal number, right? If I wrote 1000, that could be 1,000 unless I put 0b, and that's a totally different number. So we know that that would be 2 to the 3rd minus 1, so that should be 7. Right, 2 to the 0, 2 to the 1, 2 to the 2nd. That's a much different number. And of course, if I did 0x 1000, that's also a tremendously different number, because all that tells me is that I've got a 1 up there, right? If I were to write that in binary, it'd be a lot of things. 0001, 0000, 0000, That's a majorly different number. So we need to make sure that our code can understand that. All right, that's all for now. Hopefully you found this helpful. Video take 1000.